Welcome to session 1 on ARM Cortex M3. In this session, we'll be discussing about the assembly language basics related to ARM. Here, we are not going to discuss architecture, registers set or memory map. Only we are going to discuss assembly language basics required for programming. Let's begin. In assembly language programming, the instructions are architecture specific. That means each architecture will have a set of instructions and only those instructions have to be used to program the microcontroller. Every microcontroller architecture will have its own separate instruction set. So that set should be used. Here, to write in an assembly language program, an assembler is used, which is a part of an IDE. The assembler is basically a tool which converts an assembly language program to executable code. We know that whenever we want to execute the program, it should be in an executable format. So the program what we write in the assembly language program has to be converted to an executable code, and that job is done by assembler. The instructions what we use in ARM programming, the format of the instruction is first we write a opcode, or we write an instruction and opcode is generated by the assembler. Opcode is basically a unique hexadecimal code generated for each instruction, which is used during the execution by the controller. Opcode also defines the operation to be performed and the operands on which the operation has to be done. There can be different number of operands depending on the instructions. Here, in this example, there are two operands, operand 1 and operand 2. So one operand is a destination, that's operand 1 is a destination and operand 2 is a source. Like that, we can have more than two operands also. We'll see some examples in coming slides. The label which is given before the opcode is optional. Label is not mandatory. Only when we have a branch instruction or a loop instruction, usually labels are used. Comments are written for understanding so that the readability of the code increases. As I said, the number of operands depend on the instruction. For example, so there's one instruction move r0, hash 0x12. In this instruction, there's one register operand and one value. The value is prefixed with the hash symbol, indicating it's the immediate value to be transferred to register. If hash symbol is not given, then the value given will be considered as the address. If the hash is given, the value is considered as a immediate data, and that value itself will be transferred to register. So result of that instruction will be R0 will be containing 12H after execution of that. If we see the next instruction, move R1, A, where A is given in a single quotes. When we give a character in a single quote, the ASCII value of that character is transferred to the register which is mentioned. Here ASCII value of A is transferred to register R1. For ease of programming, we can also define some constants using EQU commands. Especially when we are using some constant values repeatedly in the program, instead of typing that value in the program, we use a meaningful name to that value, and that name will be used for programming. So that will increase the readability of the program, and it will also reduce the error that might happen due to typing mistakes. See here, for example, a number 0x E000 E100 is there. If we are using this particular number multiple times in the program, it may happen so that at some location, instead of ending that number with 100, if we type 010, then assembler will not show any error because it is still a valid number. But the value is wrong. It happens so that there is a mistake in the value given, but it is not logical mistake. It's a logical mistake, not a syntax mistake. So compiler or the assembler does not show the error for that, but the output what we get will be wrong answer. So it is always better that we define a meaningful name for the constant, and those names you will be using in the program. Similarly, another example is shown here to define 0x1 NVIC underscore IRQ0 enable is a name. So that name is for the some interrupt enabling. So we'll not get into details of those nomenclatures. We'll just understand that like that we can give some meaningful name to the constants. Then for defining data, whenever we want to have a lot of data operations to be performed, then there are three types of data directives or data definition directives they are called as. That is DCI, DCB and DCD. DCI is defined constant instruction, DCB is defined constant byte, DCD is defined constant data. Defined constant instruction, usually it is not used very frequently. Defined byte, that is DCB, is used whenever we want to define a byte of memory location for each character. We want to reserve a byte of data, then we will be using DCB. DCD is to define a constant values. For example, we can see here a my number 0x12345678, a number is defined by DCD. That's a defined constant number. That's a constant number which is defined. And in the next we see that there is some text to be defined. So that is done by DCB. In the text, each character stores 1 byte. That means the ASCII value of each character will be stored in the memory. So this particular string will be terminated by a null character. So it is also called null terminated string. So there's another type of assembly language that's called unified assembler language. It is slightly different from the general assembly language, but the instructions are same instructions can be used here. Only there is a small variation in the way the program is written. The advantage of UAL is that it supports both 16-bit as well as 32-bit instructions. And it helps to port between ARM and thumb mode. We know that ARM is a 32-bit and thumb is a 16-bit. So this particular instructions or this particular type of programming helps us to port between 16-bit and 32-bit instructions. So for example, if you see here add R0, R1, it performs the addition between R0 and R1 and stores the result in R0. That means it performs R0 equal to R0 plus R1. So it performs addition and stores the result in R0. If we see next instruction, wherein 3 operands are provided, R0, R0, R1. It also performs exactly the same operation. That is, it will add the content of R0 and R1 and stores the result in R0. But the difference between two instructions is, in the first instruction, the destination register is not explicitly mentioned. It is implicitly taken by assembler. Whereas in the second example, we can see that destination register is explicitly mentioned as R0, and also the sources R0 and R1 are also explicitly mentioned. So that is a UAL syntax. Whenever we write a code, if we write code 16 as a header, that directive defines it as a thumb syntax. Thumb directive implies that this is a UAL syntax. That is, code 16 defines the normal assembler language programming model, and thumb defines the UAL programming model. Like that, based on the header, we can use either one of them. So in the UAL, we can also define the width of the data what we give by applying a suffix to the instruction. So here we can see there is a .w, that's a wide type of suffix which specifies that it is a 32-bit instruction. If no suffix is given, then assembler has a choice to choose between 32 and 16-bit operations or instructions. But by default, it will always choose 16-bit. because that consumes lesser memory and it is more better in terms of code density. So by default, assembler always chooses 16-bit mode. However, depending on the tool support, some tools also support another type of suffix, that is .n, that is narrow. So .w is a wide, .n is a narrow. Okay, but this .n is not supported by all the tools, only few tools are supporting that. Here if we see the example, add s r0, #1 use a 16-bit thumb instruction by default, because we have not mentioned any of the suffix. So by default, assembler is choosing 16-bit operation. Next instruction, add.n r0, #1. This is explicitly mentioned that it is a 16-bit operation. And the next instruction is specified suffixed with a .w, and it implies that it is a 32-bit instruction. So if we don't mention anything, assembler will choose 16-bit operation. If we mention .n as a suffix, it implies that it is a 16-bit instruction. If suffix is .w, then it implies that this is a 32-bit instruction. Thank you. This is the end of first session. See you again in the next session.